All right, so now we're going to move on to ellipses, so 10-3. So again, kind of the same essential questions as for parabolas. How do we write equations of ellipses in standard form and make a quick sketch? How do we know that the equation's even an ellipse? So can we recognize that conic section and use those properties to model real life problems? So where are some of the places that you would maybe see something like an ellipse? And we are actually not going to talk about um, eccentricities for this year. We're just going to get the brief overview stuff. So basically all an ellipse is the set of all points where the sum of the distance to two fixed points is constant, called the foci. So in this little picture, those two little tacks are at the focus point. So we have some ways that we can go through and take a peek and see what's happening when we look at what an ellipse is. So it's kind of cool to take a look and watch that actually in action. So here's one kind of cool look at what it means to be an ellipse where that distance is equal. So we can take a look at that common distance going around is always the same. Another nice look to see an ellipse, and this one has dramatic music, so be prepared. So they put that fixed distance on, and then pull that out with like a pen or a pencil so you can see, and it's holding that distance fixed, so the distance between those two focus points are exactly the same. And then big action here all the way around, so it makes a really nice shape just to illustrate how that's what it means to be an ellipse. So that distance between the two foci, the sum of those distances is always the same. So it's the same distance all the way around. So you can think of an ellipse as kind of a special type of parabola, or not parabola, circle. So in a circle, those two focus points come together and make a center. So the definition of a circle is where the distance from a fixed point is constant, one fixed point. So you can think of like as these foci points get closer and closer together, you're going to have something that looks more and more like a circle and less like that kind of oval shape that we're used to seeing. But that's all ellipse is. So it's where the sum of the distances to two fixed points are equal. So good thing to sort of get in here and draw yourself a picture. So there is still a center. There's a center of the ellipse. That's not how we construct it or draw it. It's from the foci points, but there is definitely a center. And we have something called the major axis, which is the longer axis, the direction that it's longer, and the minor axis, which is the shorter one. So that's going to be telling you something about those dimensions, those lengths. So the major axis is the longer one, the minor is the shorter. They call the vertices the points at the end of the major axis. So we have those points, and then there's also the points at the minor axis as well. And we can find all these values pretty easily by looking at the equations. That's what we're going to be trying to do today. So the major axis is going to be using the A value, and the minor axis uses the B value. So we'll be able to tell what's happening and which direction is longer just by looking at that equation. So I'm going to give you some time and go ahead and pause the video as you need to. We've got standard form again. So remember there's that general form where we can tell all the conic sections can be written this way. Standard form though is the graphing or user-friendly form. So if there's a horizontal major axis, we'll look at, I guess, that top one just so we're not overwhelmed here. The standard form, if it's horizontal, the major axis is the 2a and the minor is the 2b, the length of that major axis. So notice where the a is located, the major axis, it's under the x. So if it's horizontal, it's longer in the x direction. So the bigger number is going to be under the x. The minor axis then is going to be under the y. Notice it has a center HK just like our circle. So this looks very similar. The only difference between this equation and the equation of a circle is the a squared would be the same under both of them if it was a circle, right? The distance in each direction. So that's why usually for a circle we have x minus h squared plus y minus k squared equals r squared over there, because those two denominators would be the same. We could just multiply through by it. So that's another way to think of a circle. It's just a special kind of ellipse. So it's another way to look at that value. All right, so that's our formula for horizontal. If it's vertical, super similar, except one difference. Take a peek and look through that formula and see if you can find the difference. What's the difference between the top one and the bottom one? Well, it's where the a squared is. The major axis is always the a. So if the bigger number is under the y, that means it's longer in the y direction. So that's what we're talking about when we look at these. That's what it means. So it's the same formula. The hk is still the center. It's longer in the y direction than it is in the x direction. So I have pictures down here if it's helpful for you to have a picture to kind of represent what that looks like. So I think it's really helpful, especially to note the 2A and the horizontal one is that longer, so the horizontal axis, and the 2a is vertical in the second example where we have the vertical ellipse. So we're looking at wherever it's longer, that's going to be the direction where the larger number is. So we can have those two different kind of competing looks. So in both cases, the foci are on the major axis no matter what. The relationship for the foci, c squared equals a squared minus b squared, that's that common distance that we talk about, that the distance is always the same. If the center is at the origin, 0, 0, we kind of have a slimmed down version, just like we do for circles. When we do a circle that's centered at the origin, remember that's just x squared plus y squared equals r squared. This is the same kind of deal. If the center is at the origin, that means the HK is 0, 0. So that's all they're saying, is that you can have a little bit easier version if it's centered at the origin for each of those formulas. So it's something to look for if that's happening. So we'll start with one that looks very similar to that. So this is more this general form again. So how am I going to recognize that this is in fact an ellipse and not one of the other values? Well, first thing you're going to look for is two, or one of the other conics. You're going to look for two squared terms. So we need to make sure we have two squared terms to be able to have an ellipse and not, say, a parabola, which only has one. But how do we know it's not a circle and it's not a hyperbola? I know we haven't talked about hyperbolas yet, but the reason that it's going to be an ellipse is because the two coefficients of the squared terms, they are different. So it's not a circle, and they're both the same sign. So the values are, the coefficients of the squared terms are not equal, so it's not a circle. So it's not a circle. Two square terms, not a parabola. So we're kind of doing a process of elimination here. And the signs of those coefficients, so the signs of the coefficients are the same. So that means it's not a hyperbola. If you remember the hyperbola formula, it has one of them is positive. Hyperbola can spell. One of them's positive, one's negative. So when I look at an equation like this, that's what I'm looking for. And we're going to spend some more time on that when we get to the next section as well. So it's definitely, well, all this tells me together that this must be an ellipse. All right, so how do I write the equation in a user-friendly form here? It doesn't look like I have any x's or just y terms. I don't have to complete the square. The only thing I would do is divide through so I can see what that a squared and b squared value is. Notice in your two equations, we always want it to be equal to 1. This is equal to 100. So I'm going to go through and divide everything by 100, all of my terms, so I can see what those values are. So I'm just going to reduce those fractions. So 4 over 100 reduces to x squared over 25. 25 over 100 reduces to 1 over 4, and then I have it equal to 1. So then I'm getting it into a format that's a little bit easier to deal with. So the center of this, my HK, is going to be at 0, 0. I have nothing in with the x or the y. Which number is bigger? Which one is my a squared? We'll look for the larger number. The 25 then is the a squared. The 4 is the b squared. Okay, what does that mean? That means my a value, take the square root, would be 5, and b would be 2. So it's going to be longer in the x direction. It is horizontal because the bigger number was under the x. All right, now how do we do our sketch? Well, remember the length of that major axis is just 2a. You go a in each direction. So I start at my center, which is not a point on it, but kind of like a circle. Remember how we graph a circle? We start at the center. My major axis is 5 in each direction, and my minor axis is 2 in each direction. So it is longer in that x direction. So we get that nice oval shape. That is not that bad. I have done way, way worse than that. So when we get that elliptical shape, we can tell which direction it's longer by where that bigger number is. It's under the x in this case, so it's going to be a horizontal. All right, so let's take a look and kind of do one of them start to finish where we're dealing with something, oops, that always seems to happen here, where we're dealing with something that is in general form that's not centered at the origin. So this is definitely a general form. We have all of these terms. How do we know that it's an ellipse? So let's go through that checkpoint. Think about what we talked about in the last one and see if you can figure out why this one's an ellipse. Okay, so first thing to look for, two square terms. Check. So I have that. So there's two square terms. That means it's not a parabola. Next thing to look at is the coefficients of those square terms. They are not the same. So the coefficients are not equal. That means it's not a circle. And the coefficients also have the same sign, which means it's not a hyperbola. So all of those things together tell me, yep, this is an ellipse. So every time we look at a conic section, we're going to try to figure that out. All right, now this is not in a user-friendly graphing form at all yet. So I'm going to go ahead and scooch that over for a second. We need to do some sorting and organizing. So I'm going to put all my terms with my x's together. And I'm going to put all of my terms with my y's together. And I'm going to move that constant over to the other side so I don't have to deal with that number just yet. I know it's not what I need probably for completing the square. So I'm going to have to complete the square for both the x's and the y's. And remember, whatever you do to one side of the equation, we need to do the same thing on the other side. And to complete the square, our leading coefficient has to be 1. So we kind of have everything that we need to do right now with completing the square. So let's talk about the x's first. So I'm going to look at these two terms. I'm going to need to pull out that 9 because I need to have, if I'm going to complete the square, a leading coefficient of 1. So x squared plus 9 times what would give you 36? That would be 4. So 4x, I'm just going to say plus blank. And then I'm going to do the same thing for my y's. So it's plus, so plus, I'm going to pull out that 4. Y squared minus 4 times what would give you 8y would be 2y plus blank. And then we have equals negative 4. Now on the other side, realize I'm going to do something for this first axis. So I'm going to have to do something on the other side as well. And then I'm going to have to do something for the y's. So I'm going to need to do something to compensate for that as well. Because remember, whatever you do on one side, you need to do on the other. So for me, kind of thinking of it like this, completing the square, I need to remember to do it on the other side as well. All right, so let's fill in the complete the square for each of them. Remember how we do that? It's half the middle squared. So for the x's, that would be 4 divided by 2 squared. So I'm going to do that, complete the square. And that looks like, to me, that would be 2 squared, so a 4. So I'm going to fill in that 4. All right. Now, what did I actually do? A lot of people want to immediately over here just say a plus 4. Here's the thing though, because you pulled out that 9, what you actually did, remember if we all multiply this back together, we have to get back to the original. You did 9 times 4. So what you really did is you added 36 over here. So on the other side, you have to add 36 as well. So just be careful. Think about what you're actually doing. All right, now for the y's, we're going to do the same thing. So half the middle, so negative 2 divided by 2. And then squared. So it looks like negative 1 squared, which would be 1. So what I'm adding on the inside here to complete the square is a 1. But what I actually did was a 4. I actually made it 4 bigger. So that means on the other side, I have to add 4. Just be aware, if you pull something out, I have to factor that in when I'm doing completing the square. All right, so now let's go ahead and factor. So we're going to do the x's here. So we're going to factor that. So we'd have 9 times what's binomial squared. So x looks like plus 2. And then for the y's, we're going to do the same thing. So we're going to go ahead and factor this. So y minus 1 squared. And on the other side, we just have to total up all that stuff that's happening. So it looks like we had a 4 and a negative 4 and a plus 36. So for a grand total of 36. All right, so we're almost there. What we want to do now is we want to take a peek and make sure it's equal to 1, right? Because the general form is always equal to 1. So I'm going to go ahead and divide everything through by that number on the other side, that 36. So every single term on both sides, and just reduce those fractions. So 9 over 36. That reduces down to 1 over 4. So 9 divides into 36 4 times. 4 over 36 would be y minus 1 squared over 9. And then that's equal to that 36 divided by 36, which is 1. Alrighty, so let's take a peek. What does that mean? So what does that tell us? So first of all, we know our center now. So let's get our center, HK. So careful on that. That would be negative 2, 1. So there's our center. Where's the bigger number located this time? Bigger number is under the y. So that is your a squared. And the 4 then is the b squared. So that means a is 3 and b is 2. So for our major axis then, that means this is a vertical ellipse. It's longer in the y direction than it is in the x direction. So it's an up and down. All right, so how do we make our sketch again? Well, start at the center, just like you do for a circle. So I'm going to start at negative 2, 1. That's my center. And from there, in the vertical direction, I'm going to go up and down 3. So 1, 2, 3, up. And 1, 2, 3 down. Okay, let's take a look and make sure we know where those ordered pairs are. So that would be at -2, and then if we go up 3 from 1, that would be at -2, 4, and then -2 down 3 would be at -2. So keep track of where those ordered pairs would be. And then in the x direction, we are my b values too. So 2 to the right, so that would be at 0, 1, and 2 to the left, which would be at -4, 1. So just make sure you know where those different values are. So this oval, which wasn't that good. I have a little goof on my smartboard there. This oval is slightly longer in the vertical direction. My major axis would be how many units long? Well, it's 3 up and 3 down. So my major axis is 6 long, and then it's 4 wide, 2 in each direction. So you can tell again for an ellipse which direction is longer by looking at where that bigger number is located. Tons of different examples for ellipses as well. So when you talk about orbits and looking at how different planets revolve around the sun, those are elliptical orbits. There's so many different things like that. If you've ever been to the U.S. Capitol, they have what's called a whispering room. And if you stand, and maybe you've been to one of these, if you stand at one of the focus points, because of that equal distance, it can bounce off that elliptical wall and go to the other focus point, and you can hear somebody who's whispering, even in a crowded, like the Capitol Rotunda, and you can actually hear that person talking because they're standing at the other focus point because of that elliptical quality, that distance that's equal. So lots of really cool examples too in real life that we use ellipses. So being able to recognize those, very helpful, very important. The biggest idea, I guess, is realizing two squared terms, right? Their coefficients aren't equal, so there's a different distance in one direction than the other. They're both positive, and we can tell by where that bigger number is located, either under the x or under the y, whether it's going to be horizontal or vertical. Complete the square.